The Fedorov Avtomat first appeared in public consciousness not as a tactical field tool, but as an engineering curiosity presented at the Russian Artillery Committee in 1912. Vladimir Fedorov, a 35-year-old captain in the Imperial Russian Army, stood before senior officers and demonstrated a rifle that fired continuously while the operator maintained trigger pressure, a mechanical capability that contradicted fundamental assumptions about infantry engagement. The committee members observed the weapon cycling through its magazine with methodical precision, each cartridge feeding smoothly from the curved box into the chamber, extracting cleanly after firing and ejecting without interruption. This wasn't the first automatic mechanism they had seen. Heavy rapid-fire systems had existed for decades. But it was the first designed for a single soldier to carry and operate independently. The weapon's physical appearance reflected its transitional nature between traditional rifle and automatic design philosophies. It measured 1,045 millimeters in overall length, weighed 4.4 kilograms unloaded, and featured a wooden stock extending from butt plate to handguard in classic fashion. The barrel measured 520 millimeters, providing sufficient length for powder combustion while remaining short enough for one-handed manipulation. A curved magazine protruded from the bottom of the receiver, holding 25 cartridges in staggered configuration, a capacity that seemed excessive for a standard rifle but modest for a machine system. The selector switch mounted on the right side of the receiver allowed the operator to choose between semi-automatic fire for precision shots and fully automatic fire for sustained engagement. What made the committee members lean forward wasn't the weapon's appearance, but what it represented, a fundamental shift in how individual personnel might generate firepower. Traditional bolt-action tools required 4 distinct manual operations between shots: lifting the handle, pulling it rearward to extract the spent casing, pushing it forward to chamber a new round, and rotating it downward to lock the action. A trained individual could execute this cycle perhaps 15 times per minute under ideal conditions. The Fedorov Avtomat eliminated 3 of these 4 steps, executing them automatically through captured gas pressure. The operator's only responsibility involved pulling the trigger and maintaining the weapon on target. Fedorov explained the operating principle with engineer's precision. Combustion gases diverted through a port in the barrel struck a piston connected to the bolt carrier, driving the mechanism rearward against spring pressure, while a cam surface rotated the bolt to unlock it from the barrel extension. The spent cartridge extracted, the bolt face struck a fixed ejector pin to throw the casing clear, and the return spring drove the assembly forward to strip a fresh round from the magazine and chamber it. The entire cycle consumed approximately 1/10 of a second. The committee acknowledged the engineering achievement while immediately recognizing the industrial challenge. Could local factories manufacture such mechanisms in meaningful quantities? If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Vladimir Fedorov had entered military service in 1900 as an artillery officer, but his intellectual interests pulled him toward small arms development rather than heavy cannon design. He studied at the Mikhailovsky Artillery Academy in St. Petersburg, where he absorbed both classical ballistics theory and emerging concepts about automatic mechanisms. By 1906, he had published technical papers analyzing gas-operated automatic actions, proposing that future infantry tools would eventually incorporate selective fire capability. His superiors valued his theoretical work, but remained skeptical about practical implementation. Automatic systems represented heavy machine gun territory, not individual rifle development. The institutional pressure Fedorov faced stemmed from the era's industrial reality rather than military resistance. The Imperial Russian Army had recognized the value of automatic fire since observing Maxim systems in active service. But local factories struggled to manufacture even standard Mosin Nagant rifles with consistent quality. Producing an automatic rifle required precision machining tolerances that exceeded most domestic manufacturers' capabilities. The bolt carrier group alone demanded surface finishes and dimensional accuracy that local arsenals could achieve only through hand-fitting individual components, an approach incompatible with mass production. Fedorov understood that demonstrating a working prototype meant nothing without solving the manufacturing problem. The ammunition constraint emerged as Fedorov's most pressing challenge. European powers were beginning to experiment with intermediate cartridges, rounds more powerful than pistol ammunition, but lighter than full-power rifle cartridges, specifically for automatic platforms. The German 7.922 33mm Kurz wouldn't appear until 1943, but engineers across Europe were already recognizing that existing rifle cartridges generated too much recoil and barrel pressure for sustained automatic fire from shoulder-fired tools. The standard 7 MIG-62 654mm cartridge produced punishing recoil in automatic mode and created extraction difficulties due to its rim design. Fedorov needed a cartridge with moderate pressure characteristics, rimless configuration for reliable feeding, and manageable recoil impulse. Fedorov's solution emerged from an unexpected source: Japan. The two nations had been involved in a major geopolitical conflict from 1904 to 1905, resulting in a local setback, but establishing diplomatic and commercial relationships. Japanese arsenals manufactured the 6.54 50mm with Arisaka cartridge for their Type 38 rifle, a round with significantly lower recoil than local ammunition while maintaining adequate ballistic performance for military applications. More importantly, the cartridge featured a rimless design that fed smoothly from box magazines and generated chamber pressures well within the tolerance range for automatic cycling. The government had purchased substantial quantities of these cartridges and Type 38 rifles to supplement domestic production during supply shortages. Fedorov recognized the strategic advantage in this arrangement. Instead of waiting 5 to 7 years for domestic industry to develop and manufacture appropriate ammunition, he could design his automatic rifle around an existing cartridge with established supply chains. This decision invited criticism from traditionalists who viewed dependence on foreign ammunition as a strategic vulnerability. But Fedorov calculated that a functional automatic rifle in 1916 provided more military value than a hypothetically perfect one in 1922. The engineering challenge shifted from solving fundamental operating principles to adapting known mechanisms to work with available resources, exactly the type of problem engineers had mastered through decades of working within industrial constraints. The gas operating system Fedorov developed for his automatic rifle borrowed conceptual elements from earlier designs while incorporating refinements that addressed specific reliability challenges. The fundamental principle involved diverting a portion of propellant gases through a port drilled in the barrel approximately 200 millimeters from the chamber. These gases entered a cylinder housing a piston mechanically linked to the bolt carrier. As expanding gases pushed against the piston face, they drove the entire carrier assembly rearward while the projectile continued down the barrel toward the muzzle. This timing proved critical. The bolt had to remain locked until chamber pressure dropped to safe levels, requiring precise positioning of the gas port and careful calculation of piston mass. The rotating bolt mechanism represented Fedorov's most sophisticated engineering achievement. Rather than using a tilting bolt or straight blowback system, he designed a bolt head with multiple locking lugs that rotated into recesses machined in the barrel extension. A cam track cut into the bolt carrier forced this rotation during the carrier's rearward and forward travel, As the carrier moved backward after firing, the cam track guided the bolt through a quarter-turn rotation, disengaging the lugs from their locking recesses. This rotational unlocking distributed mechanical stress across multiple engagement surfaces rather than concentrating it on a single point, reducing the likelihood of bolt failure under sustained firing. The extraction and ejection sequence required meticulous timing to prevent cartridge failures. The bolt face featured a spring-loaded extractor claw that gripped the cartridge rim during chambering. As the bolt began its rearward travel, this claw pulled the spent casing from the chamber while the case walls were still expanded from firing pressure. Fedorov designed the extraction cam profile to begin this movement gradually, allowing the brass casing to contract slightly before full extraction force applied. Too rapid extraction would tear the case head from the body. Too slow would allow residual pressure to resist extraction entirely. A fixed ejector pin positioned on the left side of the receiver struck the cartridge base as it cleared the chamber mouth, pivoting the case around the extractor claw and throwing it clear through an ejection port. The magazine system presented unique challenges due to the Arisaka cartridge's bottlenecked configuration. Rimless cartridges require carefully calculated feed angles to prevent nosediving or rim override malfunctions during chambering. Fedorov designed a curved, detachable box magazine with 25-round capacity, the curvature matching the natural stacking angle of tapered cartridges. Internal follower geometry and spring tension were calibrated to present each round at precisely the correct angle for the bolt to strip it smoothly from the magazine lips and guide it into the chamber. The magazine catch mechanism allowed rapid replacement while maintaining sufficient retention force to prevent accidental release during operation. The selector mechanism gave the operator control over firing mode through a simple rotating lever. In semi-automatic mode, a disconnector interrupted the trigger-sear relationship after each shot, requiring trigger release and re-engagement for subsequent firing. In automatic mode, the disconnector disengaged entirely, allowing the weapon to fire continuously as long as ammunition remained and the trigger stayed pressed. This selector system added complexity but provided tactical flexibility. Semi-automatic fire for aimed shots at individual targets, automatic fire for suppressive applications or close-range situations. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. Testing the Fedorov Avtomat revealed challenges that couldn't be predicted through theoretical analysis alone. The first prototype trials in 1913 demonstrated that the weapon functioned mechanically but exhibited extraction problems under certain environmental conditions. When firing in cold weather, the steel components contracted at different rates than the brass cartridge cases, occasionally causing extraction failures as the case body gripped the chamber walls more tightly than expected. Fedorov addressed this through careful chamber dimension adjustments and extractor spring modifications, but the solution required extensive empirical testing rather than mathematical calculation. Each modification needed validation across temperature ranges from -30 to +40 degrees Celsius. Barrel heating presented another unexpected complication. The Arisaka cartridge produced less heat per shot than standard local ammunition, but sustained automatic fire concentrated thermal energy in the barrel faster than traditional rifles experienced. After approximately 100 rounds of continuous firing, barrel temperature exceeded levels where steel properties began changing, affecting accuracy and potentially causing dangerous pressure spikes. Fedorov couldn't simply increase barrel thickness, because additional mass would make the weapon too heavy for practical field use. Instead, he refined the gas port positioning and piston mass to reduce the cyclic rate from approximately 600 rounds per minute to roughly 400, decreasing thermal buildup while maintaining effectiveness. Magazine reliability demanded obsessive attention to dimensional tolerances. The curved magazine body had to flex slightly during loading and firing, while maintaining precise lip geometry to present cartridges at the correct angle. Too much flexibility caused feeding malfunctions. Too little caused magazine insertion difficulties. Fedorov tested dozens of spring materials and follower designs before achieving consistent reliability across the magazine's capacity range. He discovered that follower tilt during the final few rounds, when spring pressure was lowest, caused more feeding problems than any other single factor. The solution involved redesigning the follower profile to maintain parallel alignment with the magazine walls throughout its entire travel range. Field testing with military units revealed human factors that bench testing couldn't simulate. Personnel accustomed to bolt-action rifles initially struggled with the Avtomat's cyclic operation, particularly the importance of maintaining consistent shoulder pressure to control muzzle climb during automatic fire. The weapon's recoil impulse felt different from bolt-action rifles, not stronger, but more continuous, creating a pushing sensation rather than discrete jolts. Training protocols had to be developed specifically for automatic fire discipline, teaching users to use short bursts rather than emptying magazines in single trigger pulls. Production testing exposed local manufacturing limitations. The Tula arsenal could produce perhaps 30 to 50 Avtomats monthly using existing machinery and skilled labor, compared to several thousand standard rifles in the same period. Each Avtomat required approximately twice the machining time of a standard rifle, with critical components like the bolt carrier group demanding precision that only experienced machinists could achieve consistently. Fedorov recognized that mass production would require specialized tooling and training programs that the current industrial capacity couldn't support. The weapon worked brilliantly as an engineering achievement, but remained practically limited by the infrastructure available to build it. The final curiosity that defined the Fedorov Avtomat's existence emerged not from its mechanical design, but from the strategic calculation underlying its ammunition choice. By selecting the Japanese 6.5 Kix 50mm Arisaka cartridge, Fedorov created a tool that could exist immediately rather than theoretically. This decision revealed deeper insight than simply accepting foreign ammunition as a convenience. It demonstrated understanding that engineering advancement often requires working with available resources rather than waiting for ideal conditions. The Arisaka cartridge possessed characteristics that made it inadvertently superior for early automatic rifle applications compared to contemporary European military ammunition. Its moderate powder charge produced chamber pressures around 3,200 bar, compared to the local 7.62 kSp 3,900 bar, reducing mechanical stress on the bolt and barrel during sustained automatic fire. The rimless design eliminated the rim override feeding problems that plagued rimmed cartridges in box magazines. The relatively light projectile weight of 139 grains generated manageable recoil impulse while maintaining flat trajectory out to practical engagement ranges. Most significantly, Japanese manufacturing quality control produced ammunition with consistent powder charges and primer sensitivity. Variations that could cause cycling problems in automatic mechanisms were minimized through industrial precision. Fedorov recognized that ammunition consistency mattered more for automatic platforms than for bolt-action rifles. A bolt-action operator could manually clear a misfire or extraction failure and continue within seconds. An automatic rifle experiencing the same malfunction would cease functioning entirely until someone manually corrected the problem. This vulnerability to ammunition variation meant that automatic systems demanded higher quality cartridges than contemporary military procurement standards typically provided. Japanese ammunition manufacturing met these requirements not through specific design for automatic fire, but through general industrial sophistication in quality control processes. The geopolitical dimension of this choice carried implications beyond engineering considerations. The dependence on foreign ammunition for the Fedorov Avtomat created a supply vulnerability that planners found uncomfortable. If diplomatic relations deteriorated, cartridge supply could be interrupted, rendering existing tools useless. Fedorov argued that this risk was acceptable, given the weapon's limited production numbers and the immediate tactical advantage it provided to equipped units. He further noted that by the time production might scale to levels where ammunition dependency became strategically significant, local industry would have developed domestic alternatives. The weapon served as a functional prototype for automatic doctrine rather than a permanent solution. This ammunition decision also revealed Fedorov's understanding of how technological innovation actually occurs in military contexts. Waiting for perfect domestic ammunition would have delayed automatic rifle development until well after the major global conflict of the 1910s concluded, by which time institutional memory of the weapon's potential advantages would have faded. By creating a working example that personnel could test under field conditions, Fedorov generated empirical data about automatic rifle capabilities that informed future development regardless of ammunition source. The weapon's existence proved the concept viable, making subsequent investment in appropriate domestic infrastructure justifiable based on demonstrated results rather than theoretical promises. The Fedorov Avtomat's legacy extends beyond its limited production numbers or tactical impact. Approximately 3,000 were manufactured between 1915 and 1925, a quantity insufficient to influence major history-altering events, but sufficient to demonstrate automatic rifle viability to observers worldwide. Various forces employed small numbers during internal conflicts and border engagements, but the weapon's greatest contribution involved proving that individual personnel could effectively operate selective fire tools that previous doctrine had reserved for crew-served heavy systems. The design influenced subsequent automatic rifle development in subtle but important ways. Engineers studying the Fedorov Avtomat during the 1920s and 1930s absorbed lessons about gas system timing, bolt rotation mechanics, and magazine geometry that informed later projects including the AVS-36 and eventually the Kalashnikov system. The Japanese connection particularly intrigued designers, who recognized that Fedorov had solved the intermediate cartridge problem through procurement rather than development, a strategy that accelerated fielding by years. When local planners later developed the 7.62-39mm M43 cartridge for subsequent platforms, they were addressing the same fundamental challenge Fedorov had circumvented through the Arisaka adoption. The weapon's historical significance lies in demonstrating that innovation timing matters as much as technical perfection. Fedorov could have waited for ideal conditions, domestic ammunition production, improved manufacturing infrastructure, refined doctrine, but chose instead to create a functional tool using available resources. This approach meant accepting compromises, foreign ammunition dependence, limited production capability, and uncertainty about employment tactics. Yet these compromises enabled personnel to experience automatic capabilities in 1916 rather than 1936, generating 20 years of empirical knowledge that informed all subsequent development. Modern firearms historians recognize the Fedorov Avtomat as the first practical automatic rifle deployed in service, preceding the Browning automatic rifle by 2 years and the German Sturmgewehr 44 by nearly 3 decades. This chronological priority reflects Fedorov's engineering philosophy: build what can be built now, rather than wait for ideal conditions that might never arrive. The weapon's technical specifications seem modest compared to later automatic designs, but context matters. In 1916, creating any functional automatic rifle represented a revolutionary achievement regardless of the ammunition it chambered. The Fedorov Avtomat taught engineers worldwide that automatic rifle development required thinking beyond traditional design parameters. Chamber pressure, extraction timing, gas port positioning, magazine geometry, and ammunition consistency all demanded reconsideration when mechanisms cycled automatically rather than manually. Fedorov's willingness to use Japanese ammunition demonstrated that these problems could be solved through creative resource utilization rather than waiting for comprehensive industrial development. His weapon exists now primarily in museums, but its influence persists in every modern automatic rifle that applies lessons Fedorov first discovered through pragmatic engineering necessity. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.